All right. So, everybody, welcome to session 4 of Learning Labs. So today, what we're going to be going over is we're going to be going over our first algorithm. So up until this point, you guys saw a lot of like rotations around block spheres and matrices and matrices and just a whole bunch of stuff that's like, okay, yeah, this is cool. What the heck does it actually do? So today, we're going to give you our first example of that. So today, we're going to be going over what's known as the Deutsch-Jozsa algorithm. So this is a Boolean input and output function, and we'll be going over through some of the specifics of it today. So let's start. So once again, we're going to be referring to the Qiskit textbook because it is a very good resource for several different topics in quantum computing, and we'll be doing a walkthrough of most of the section today. So in essence, the Deutsch-Jozsa algorithm is the first example, the first one that was discovered, the first algorithm that really showed how a quantum computer can do better than a classical computer in some scenario. So it showed that there can be advantages to using a quantum computer for some specific problem. So what we're trying to do here is find whether we have this thing that's known as an oracle. And so you can kind of picture it or think of it as like a black box, like you put a number in. You might have learned this in elementary school, like you put a number in and it spits a number out, or several numbers in and it spits another output out. So that's what this is. So we are given a hidden Boolean function f, which takes a string of input bits. So this is a sequence of zeros and ones, and returns a 0 or a 1, a single 0 or a 1. So that is this over here. That's this Deutsch-Jozsa problem. So the property of the given Boolean function is that it is guaranteed to either be balanced or constant. And so what those two things mean is for every single input, so if you have a sequence of, say, for example, 3 bits, there are 8 different inputs. So for 3 input bits, there are 8 different sequences you could put into this function. For every single one of them, is it going to output 0 or 1 for everything? That's what it means when it's constant. For every single input, it's going to output the same thing. And balanced means, will it be exactly half 0 and half 1 for all the given inputs? So how are we going to find that? So classically, let's take a look at this. So say, for example, we have our bit sequences. So give me a second. Let's write out all the different combinations for 3 bits first. So we have bit 0, bit 1, and bit 2. We have 0, 0, 0, 0, 0, 1, 0, 1, 0. We have 0, 1, 1. We have 1, 0, 0. We have 1, 0, 1. We have 1, 1, 0. And finally, we have 1, 1, 1. So we have 8 different bit sequences. And so what we want to know is just give me a second. I lost my train of thought. Yeah, so if we have this classical scenario, what we can do is look at the outputs. We plug these in manually, each one of these in manually. So if we have f of bit 0, bit 1, and bit 2, then our best case scenario for this is by checking at least 2 to the power n divided by 2 plus 1 inputs to see if the oracle is constant or balanced. So can anyone tell me why they would think this would be in the classical case? Does anyone, you guys can take a minute to think about it, and yeah.
They might not completely understand that.
Is anyone having trouble understanding anything? Or that is the number of times it would take to determine whether this oracle is a constant oracle or a balanced oracle. So that is, will it output always the same thing, or will it output 0 part of the time and 1 part of the time? Well, rather 0 half of the time or 1 half of the time. So this is just the problem that is given. This is the problem statement.
The oracle is the black box function.
Yes, it is a black box function in this case. And so in this case, you know what? So this is just a bunch of letters and stuff. Let me actually work through this example. So, or, you know, you guys can think, but I'll just give you guys a number for now. So 2 to the power n. So in this case, we have 3 input bits where n is the number of input bits. We have 2 to the power 3 divided by 2 plus 1, which is equal to 5 times we have to try. Okay. Now you guys can think about it a bit more. Yeah, n is the number of input bits. Sorry, I didn't specify before.
Oh, so that's one thing. And anytime you see quantum, like an algorithm or anything, really, if you see lowercase n, that is going to equal the number of qubits that we're working with. Okay, and then you'll see 2 to the power of n, like 2 to the power of lowercase n, and that is like the number of classical bits can represent. Does that make sense?
Yeah.
So and you'll see that represented as big N. So big N is equal to 2 to the power of little n. And this is like the mathematical way to represent this, and it's you might be able to understand this once you get used to this format. But if it helps, I can explain it in a slightly different way.
Yeah, go for it.
What we're doing with Deutsch-Jozsa is, this is not some algorithm that just solves something like a regular problem that you guys are used to. What that means is that our question is about a given function. So function, literally like f of x is equal to 1 minus x. That is our function, okay? So we're gonna think about this classically, okay? So if I have that function, okay, do you know what the input can be? If I say the input is one thing, right, which a binary number, so 0 or 1, and the output can be also 0 or 1, because they're just going to deal with 1 bit so far. So if I didn't know the function, right, I could have 2 possible inputs, 0 and 1, and depending on that, my output could be 0 or 1 respectively, right? So we don't know what our function does now. I gave 1 minus x as an example, but let's say we just have a function f of x, okay? We want to know if this function magically turns our input always to 0, always to 1, or 1 half the time and 0 half the time.
Yes.
Does that make sense? Why it would be called constant or balanced? And we don't care what the mathematical definition of the function is for now. It could do some magic, like multiply the number by 0, right? That would always result our function output would always be 0, right? And that would be a constant function. It would constantly be 0. So in general terms now, Deutsch-Jozsa, this algorithm, it says if you give me a function, I will figure out whether that function's output will be constant or balanced. Does that make sense?
Okay. Yeah. So continuing off of what Sarvesh just said, I can explain to you guys why it would take 2 to the power n divided by 2 plus 1 tries. So say, for example, we have f of 0, 0, 0, and this outputs 0. Similarly, we have f of 0, 0, 1, outputs 0. F of 0, 0, oh, sorry. F of 0, 1, 0, that outputs 0. F of 0, 1, 1, and this outputs 0. Okay, so up until this point, the function is, so far, it's constant, right? So we can, so it's either fair game that it can either be constant or balanced up until this point. But the next input that we try is a determining factor. So if we have f of 1, 0, 0, if this is 0, then we say it's constant. Hold on. Yes, exactly. So, sorry.
So,
Yeah.
Yeah, but there's one thing I want to say. This, okay, so for multiple bits like this, George shows the algorithm is going to tell you if the algorithm is constant or not constant, okay? When we're dealing with one bit, it's either constant or not constant, meaning that there can be, if I guess 50% chance, or sorry, 20% of the time it's a 0, 80% of the time it's a 1, if you're dealing with multiple bits, right? So with one bit, it is either constant or balanced, but for multiple bits, then Joy shows the algorithm tells you if it's constant or if it's not constant. We don't know if it's balanced, right? So when Aditya was giving the example, if he includes that other input where the first, the leftmost bit turns into a 1, if it's a 0, we don't know yet that it's constant, but if it's a 1, then we know that it's not constant. Does that make sense? Like one.
But if it's the one that isn't balanced, if it's not constant, the rest are 0, right?
Because I guess later on, we don't know this function, right? I guess it was explained. Does that make sense?
Yeah. So in this case, one of our constraints is we are assuming it is either balanced or constant and not really anything in between.
Yeah. So that is an assumption we're making. So this does not, I guess, yes, there are more functions out there, and for those, you either have a constant or non-constant, right? And in this example, he applies that extra constraint that it'll either be constant or balanced.
Yeah.
So if we get a 1, then we know that it is balanced, right? Because there's no, he's applying a constraint that there's not like 80%, right?
Yeah.
And if we get another 0, we know that it's not going to be that percentage, so we know it's going to be constant. And this logic works out when we're first going to be dealing with this one bit, which is called a single bit function.
Yeah. So.
And this will be the exact case.
Yeah.
Either have 0 or 1.
What's the difference between the single bit and the multiple bit?
Okay. Yeah. I mean, a single bit function is going to be that your input.
Try to speak about it.
Your input is going to be a single bit, and for a multi-bit function, your input is going to be multiple bits.
Yeah.
So not just one. That's all the distinction there is. That's all there is for now. And yeah. So whenever we do our examples, when we do this, we're going to be dealing with one bit before we extrapolate.
Yeah, before we talk about 2 inputs and 3 inputs, because then our oracle starts to get a bit more complex in terms of the gates we use.
Yeah. So okay, good question. So let's say, okay, for this example, it'll be multiple bit inputs, so that's clear to see the pattern. So if I have 3 input bits, okay, and we want to know, remember, this question is about the output of the function, right? Output of the function is going to be 1 bit, okay? Is it going to be 0 or it's going to be 1? Okay. Let's say I need to try, so we have 3 input bits, correct? So that is our small n, correct? So we have n is equal to 3, okay? Now, if I want to try, if I'm saying I want to try all the possible inputs, there are 2 to the power of n possible inputs, correct?
Why can I divide everything by 2 and then add 1 and be like, oh, now I can conclusively prove that this is.
What it really boils down to is that we are dealing with a function that either outputs 0 or 1 all of the time, or 0 exactly half of the time, and 1 exactly half of the time. So we aren't going to have something that outputs like 0 5 times and 1 3 times. It's exactly going to be half of the time each.
So basically, this function is number.
Sorry.
We can tell if it outputs 0 all the time, or if it's
Yeah.
Yeah.
and then this is what Joyce showed us.
Yes, this is what Deutsch Jose does. So our oracle in this case is either constant or balanced. It's either going to output 1 all the time, 0 all the time, or 0 half the time and 1 half the time. That's it. That is one of the constraints of this problem. It can't be anything else.
Okay. Okay, no, that's perfectly valid
Yeah.
question. Okay, so first let's make sure that we're not getting confused, because I realized I might have been confusing about this. Deutsch, Jose, we have not even started that algorithm. We are simply saying what it is trying to, what is the question it's trying to solve, okay? So what a constant function means is that it is a function that either does, it is the same input all the time. So it's always 0 or always 1. Okay, so those are same output every time. Exactly. So the reason we have to, there's only 2 options. It can be the same output all the time, or 0 half the time, or 1 half the time. So to validate whether what function we have classically, right, you would check half the input, like half the input, and then check once more. Worst case, that's what we're saying.
Yes. And yeah, I should have said worst case more because
Yeah. Oh,
yeah.
no.
Yeah, we can have another case where it's like, if you have 0 1 0 1 0 1 0 1, then you would only need to check twice to know that it's balanced.
So this is the worst case. You will have to check half the time, and then if you still don't know if it's like been all zeros up till then if you do 1 more, that'll give you your answer.
Yeah, so I should have, so can I write it on there? Because then it'll be more clear.
I thought you had to check like every.
No. Okay,
God, my
I'm glad
handwriting.
that got cleared out. There's probably a question
Yeah.
for a lot of people then.
Thank you for asking that question because no. Thank you, actually. You're making a clarifying point.
We are just trying to understand this. No? Okay.
Okay. So this is the classical case. It is solved in this number of tries worst scenario. Now, let's move on to the quantum case. Yeah. Wait, one more time?
Like, I would explain like how we even turn a function into quantum.
You know what? I'll let you do that
Okay.
part.
Okay, so one of the first things about quantum is that anytime we have a problem that we want to solve in a quantum way, we have to make sure not to get ahead of ourselves, right? If I give you a problem, if I ask you a question in Spanish, I ask you to solve it, you might be like, oh, okay, I'll solve it because I know the instructions. I first have to translate that to you, right? You have to translate it to English, right? The same thing. If you can explain a problem to me classically, right? That question, you have to translate that to something a quantum computer will be able to understand, right? So one of the things we just talked about is our question is about a function. Okay, so how do we turn that function into something a quantum computer can understand? Okay, and this is what our oracle is. Okay, so you will see an oracle defined as, in notation, it'll be like U, okay? And that is going to be our oracle name.
Yeah, so yes,
Yeah.
we're gonna get to that.
And why are they the same? Well, because if we translate the oracle into like quantum gates, it'll eventually just become a unitary matrix. Does that make sense?
A unitary matrix is what you can use to manipulate qubit states.
Oh, yeah.
So they're going to be valid gates that we can use.
Yeah.
But you can also combine multiple gates to create a bigger unitary. Okay, it's just another term for it.
Yeah, unitary matrix is the platform which we use to build gates.
Querying the oracle thing we talked about at the.
That's
You know,
that was Grover's. This is a different one. Grover's is a bit more advanced, and we will probably get to that in a few weeks.
Yeah, that's.
So you see, you have an oracle, right? So oracle is going to define the problem to the quantum computer.
Yes, and in general, when we talk about oracles here, it's mostly going to refer to a unitary matrix of some kind.
So, yeah, question?
Yeah, this might be a little bit dumb, but what's the circle cross thing?
Oh, we're gonna go over
That
that.
is exactly what
Yes,
it is.
and you know what? Keep asking these quote unquote dumb questions because they are not dumb. They are the stuff that we need to address and we will address.
Yeah. So, firstly, I'm going to explain what's on the Qiskit textbook. So in case you guys want to go home and read it, you guys will actually understand it.
First of all, let's go over two things. Let's go over the notation. So that's the plus in the circle and the cross in the circle. And then let's also go over modular arithmetic, which we're going to need.
Yeah.
So real quick, before we get to the quantum case, we're going to do a little bit of an intermission here. So we are going to first start off by addressing some notation things. So you guys have seen this symbol already. And you guys have also seen this symbol already. But what do both of them mean? So this is the symbol we use when we want to tensor matrices. So for example, if you want to combine qubit states into one matrix, or you even want to combine unitaries into a single matrix, this is what you can use. This is the tensor. And this modular thing, you see it in the CNOT gate. You have like the little control qubit and the target qubit. So the target qubit has this symbol on it. This is what's known as an XOR. And even these two can be used in classical computing, and you may see this in other fields of math as well. So these two are elementary operations. So tensor, real quick, we'll just do a review from last time, what both of these operations are. And so if I have two matrices here, so say I have A, B, and I want to tensor them to C, and I want to tensor this by CD. So I said one thing last lecture that wasn't correct, and that was these two need to be the same dimension. They don't need to be the same dimension. They can be arbitrary dimension. So what that means is basically you can take one element of the first one and multiply it by the entirety of the matrix for the second one. Similar case for B.
This is the distributive matrix multiplication that
Yes.
we wished it was as simple. But yeah,
Yeah.
it's just like the distributive property.
Yeah. It's more intuitive when you first encounter matrices in whatever algebra class you did it in first. And so naturally, this will expand appropriately. So we have AC in the first element, AD in the second element, BC in the third element, and BD in the fourth element. So does this make sense to everybody? How you tensor matrix? Yeah, what's up? Yeah, it's almost like, you know, the first matrix is, you know, a set of coefficients that you want to multiply the second matrix by. I'll give you guys a minute to write this. Any more questions? No? How are you guys' day? Good? Are,
I would just do for water. Is it possible to have matrices?
do you guys want me to do an example that, you know, doesn't have both of them that are the same dimension? Okay,
We'll
A,
but
B.
just work with, I mean, you can do that if you want. I was just gonna stick to column vectors for now.
I-
Cause that's all that matters.
I know, but I'll just give a quick example. It's not gonna take that long anyway. So, oh, we're gonna see that in a minute. Don't,
Yeah,
Like
so,
column vectors,
Oh,
only
like
when
the
you-
state, you know, the state is like the-
yeah, so do you guys remember when we said a state is literally like this? Or it's like 0, 1, 1, 0 or something? So when if you tensor two states together, right? It'll give you so right here, we tensored two,
oh, my fault, yeah.
we tensored two states together, we get this, right? Now we have 4 entries, okay? All this is doing, right, is just mathematically joining these 2 qubits into one circuit. So in the quantum lab, you just say you initialize 2 qubits. When you initialize 1 qubit, you just have this. So when you initialize the second one, you have to tensor their matrices together. So now you have one state that represents the entire circuit.
Yeah,
Does that make sense? Okay. That's all the tensor does.
So to recap, the tensor basically allows you to take 2 different.
Yeah. Yeah, so with the math, right, you wouldn't want to be working with like multiple separate matrices, right? If I'm saying I have a quantum circuit with 5 qubits, I wouldn't want to do separate operations on separate things. So when you tensor each of those qubits together, you get a combined matrix, or it'll be a column vector, but still matrix that will have, it'll contain the information on what's happening on all 5 of those qubits.
yeah,
Right, and now you can, to do an operation on them, you can just apply one matrix to that column vector, and that is your overall circuit state, instead of just state of one.
all right. So here's a case where, here's a case where both the dimensions aren't the same. Does anyone have any questions about it? Does it kind of make sense? All right, cool. So that's tensoring matrices. That's what that logo pretty much means. And now we're going to go over what the plus in the circle means. So that is XOR. So what we are going to be seeing here shortly in the Deutsch-Jozsa algorithm is we're going to be seeing what's called modular arithmetic. And this is, we're going to be looking at the mod 2 in this case. So has everyone here heard of the modulo operator before in computer science, basic programming? Yeah, so that's basic.
Percent sign, yeah.
Yeah.
The remainder.
So basically, if you take a number divided by another number, there's how much you have, and then there's how much is remaining. It returns the remaining quantity is all. Okay, so basically that gives us 4 cases. So we have,
Yeah, and you'll see that,
So like one XOR one would be zero. Something like that.
Yeah.
It's called a.
oh, yeah, when we talk about like gates like this, or like even stuff like a NOT gate, there's no special rule that it changes to classical stuff. Only reason there might be a change is because we are applying those gates or logic gates to quantum situations. But if we're doing XOR on 0 or 1, everything is the same as classical.
Yeah.
yeah, and so in this case, for modular arithmetic, if we have 0 plus circle thing, I don't know, 0 mod 0 is 0, 0 mod 1 is 1, 1 mod 0 is 1, and 1 mod 1 is 0. Does this make sense to everyone? Yes, it's modular. Yep, that's all.
And it's like that for,
Just carry over to, like,
binary.
this,
Um,
larger and
like history?
I mean, yeah, it will be, but we won't be looking at that today.
I was just-
I did do this, like, my homework really weeks ago.
We're gonna be building off of those.
Yep. Okay. So now with these two tools in mind, we can look at the quantum case for this algorithm. So, well, let's first start off with how many times we need to query the oracle, and then we can talk about the oracle itself. So in the previous, in the classical example, we needed to query the oracle this number of times. 2 to the power n divided by 2 plus 1. In the quantum case, you need to query it one time. That's it. Yep. One query. Yeah, one time. That's it.
Wait, that's the worst, that's like one time.
Worst,
one
best,
time
everything.
Yeah, so
Is it
whenever,
like a band?
one time.
Yep, worst, best, everything.
Yeah, so this is like the first algorithm where you'll see, and you guys will be able to build this, right?
In
Once we
Qiskit.
talk about it, where it's like, okay, quantum computers are provably faster than regular computers at a problem. Okay? So yeah, this is where the coolness
Yeah.
begins.
Yep. This is where I like that. This is where the coolness begins. It was-
Oh, yeah, we will, that's what he's gonna go over.
yeah,
like, right now.
don't worry, we're gonna
Some
go,
symbols, and now we're
yeah,
gonna-
all these complex symbols, scary stuff.
Yeah,
I mean, it's Halloween. We're looking at scary stuff before Halloween comes around. So yeah. Anyway, so let's go over the quantum solution. So using a quantum computer, we can solve this problem with 100% confidence after only one call to this function, provided we have the function f implemented as a quantum oracle. So in this case, we're using a unitary matrix, which maps the state of x, and I know it says x ket, y ket up there, but you can throw a tensor between them and it'll mean the same thing, to x ket tensor y modulo f of x. And in this case, f of x is our oracle. So you take that certain number of bit strings, put it into x, and it'll either return a 0 or a 1. So where this plus with a circle is addition modulo 2. And below is a generic circuit that can be given for this problem.
Wait, what's the zero to the X or N?
yes, we'll get to that. So, yeah, we're gonna get to that.
Yes,
Good question.
it is a tensor.
Oh.
We're just tensoring gates in this
Yeah.
case.
You said XOR? Where'd you see the XOR? The one in the Oracle?
Oh, wait, not X.
Yeah, keep in mind, those are two very different symbols.
Yeah.
Right?
Yeah.
So, yeah.
Yeah.
Talking about the tensor. Okay, yeah. Oh, we haven't explained that, that's the thing. Right now, that's what we're explaining right now.
I just won't ask any questions.
No, you guys, bring it, if you guys can ask questions, but the thing is,
Again, this is
Yeah.
split over 2 sessions. So if you guys have any questions in between, feel free to shoot them our way. And if you guys want to take a look at this in the meantime, before our next session, you guys are always welcome to do that as well.
so we're going to look at this, okay? So that we have a sense of beginning and end, we're gonna look at this from left to right, okay? So if you guys recognize these two lines, those are like the circuit lines,
Yeah.
right? So we have this monstrosity over here, 1, right? We have this line. So what we're gonna be doing is applying gates to these, and we will explain what each of these things are.
Yes.
So,
So first of all, let's start off with what this means over here. We have 0, and then we have this tensor power thing, whatever that means. So basically what this is we have a quantum register with n bits, and we want to start off with that number of qubits. So if we have 3, we want to have a 3-qubit quantum register. So instead of it being only 1 0, we'll have 3 qubits that are initialized to 0, and then we just have this one down here as well. And if it's 5, this will be 5 0 qubits starting off, whatever the case may be.
Are quantum registers used in the same sense as classical registers are as actual memory, or no? Like
No.
just like an analogy.
It's
in this case, a register is, so, okay, a register in classical computing is a collection of, it's this,
It's like a temporary memory storage. thing.
Yeah.
Yeah.
So a register in this quantum sense is going to be a collection of qubits, like a group. Okay.
Yeah.
And okay, this tensor and stuff. Remember how I said tensor product is basically multiplication, right? So if I wanted to tensor product a state multiple times, that means I have that qubit state multiple times, right? So I would say I want the state as 0. I would say to the power of n, right? But if I do that mathematically, that's like, oh, 0 to the power of n. That's, we don't know that we're dealing with tensor product, so that's why you put this symbol there. Okay, so this all it's saying is we're initializing n number of qubits in our quantum circuit. Yeah, that's
Mhm.
all that's saying.
Yep,
okay?
that's all that means.
And in our algorithm, right, in our basic version, we are going to say that, which is called, that's called the input register. We're
Yep.
calling that as just 1 bit. So here, anytime you see lowercase n, that is going to be a 1.
So those are qubits,
Yes,
both of them. The 1 and the 0 to the.
exactly.
Yeah.
So so this is one
Yeah.
register. This is just a single qubit.
Yeah.
A single qubit register.
That's initialized to 1.
Yeah. And we know the 1 same 0.
After the Hadamard gate.
Huh?
Yeah, the input register is initialized to all 0 and the output is registered to 1. And there's this weird thing where at the end you measured,
That why the output?
no, and this is what I'm explaining now. It's a weird thing where you measure the input register instead of measuring the output register. I don't know why they call them the way they do, but your final result is essentially going to come from the input register and not the output register.
Or
Why
this.
does it say X over there and also X over there.
For what?
For both sides, it says X over there.
This one?
For the Hadamards?
No, for like this
Oh,
branch
this.
has an X and then that other branch has an X.
Okay, okay. Good question. So in a circuit, right? Oh, okay. How about this? Let's go to this Hadamard and then we'll get to Oracle. Right?
Okay, yeah. I'll
So-
just let you explain all
No.
it and just not.
No, okay. Yeah. Well, how about this? You can ask questions after each checkpoint.
Okay.
Yes.
Until then. Okay, so now the Hadamard, okay? Based on what we said here, what do you guys think this?
There's 8 Hadamard gates for each of the bids that we passed for those.
So we just apply a Hadamard gate onto all the qubits that were here. Now I see those.
Have 0, have 1 probability.
There you go.
Yeah, pretty much.
And then for this qubit,
It's both, it's the same thing.
It's a slightly different state. So it's 0 ket. So for all of
It's like
these,
an alpha ket 0 plus beta
Okay,
ket 1.
okay.
Like a
let's
1 over square root of 2.
let's start off with our states. So for the input register, so our psi of 0 is equal to so we have we start off with 0, and this is for how many qubits that we have, or that should be a small one.
And plus 1 to the.
Yeah. And then we have, we can tensor this and say 1. So this is our starting off state. And then if we have psi of 1, so this is after we apply all the Hadamards. So we apply,
Wait, why is it a tensor 1?
well, this is the,
1 was the other thing.
no, the 1 is the output register.
okay, all this is saying is, these are the qubits that we are using.
Yeah.
That's all that's saying. We had a n qubit register that was in the 0 position, right? And then we had another qubit that was in the 1.
Yeah.
So you tensor everything. That's how
Oh,
you-
that's like the input state? or-
Yeah, so psi of 0 is the state that we're starting off with.
Oh, okay, yeah.
Yeah, so that's why we're denoting it as psi of 0.
Yeah,
It's the starting state. Maybe I should note that down.
State before.
Before anything is done. This is what we're starting off with.
Yeah, and how is it? Don't use the words input and output. Those are gonna be reserved for it.
Yes.
Okay, so when you say, oh, is that our input as 0 and 1? those input and output have very different meanings. Here, for this,
Yeah. So if we have, so we want to apply a Hadamard of over this, and we want to apply that to this, right? And we want to tensor that by applying a Hadamard to the one state. So this is what we want as our psi1. And so what that will give us is we will have, oh my God, that is an awful word. Oh, that's just applying the Hadamard to that number of qubits. So if we have,
the, sorry, it's why it doesn't have tensor. Because, okay, all the tensor n is saying, okay, is, so for this algorithm, what we want to initialize is an n qubit input register. Okay, I said input register, and I know why I'm saying that, okay? N qubit input register, okay, and a single qubit output register, okay? So that is just a requirement for this algorithm. We want n qubits for in one section. You can think of it as section. This cluster of qubits is just, I need n of them, right? And for our case, n is will be one, but they're describing the generic one. So n is equal to n. And then we want just one separate qubit, okay? And it is going to be in the one state. In Qiskit, yes, all of them are going to start off in 0, and then we apply a NOT gate on one of them to make it a 1. But yeah, these are just sections of qubits. Okay.
yeah. All right, so
So yeah, with the Hadamard, right? Yes, it's split across two things, right? But this literally just means apply a Hadamard gate on this section of qubits, and then apply a Hadamard gate on this qubit. So essentially, you could say apply Hadamard gate onto all the qubits that you have. Okay. And
Why is that a negative? Or no?
it's because we're applying the Hadamard to the one state instead of the 0 state.
Oh, it's phase.
Yes.
yes, you guys remember the block here that we went over? How when you do a Hadamard on 0 state, it comes here, Hadamard on 1 state goes the other way. That is a key difference, right? And we will make use of that in this algorithm. So algorithms are going to take advantage of interference and other stuff. And this is an example.
Okay. Yeah, so basically, after we go to psi of 1 and we apply all the Hadamards, this is essentially what we end up with. So we have a bunch of the qubits that are in this input register that are in the plus state, or you could rewrite this as plus, and then you want to tensor that over n qubits, and then this is now in the minus state, and that's the output register. So this is another way to write it. They're all in superposition. And then what you want to do next is apply the quantum oracle. So what that will do is whatever the quantum oracle may be, you will apply it over.
Yeah.
Do you want to?
Yeah, I'll just.
Here,
So-
come over here and speak.
Okay, so now we have the quantum oracle, right? And that's what we were saying, translate the problem into something a quantum computer can understand.
Oh, sure, I got you.
Sorry, I don't have an iPad. Okay. OneNote.
Oh, OneNote. Just double click this.
That's fine. Sorry. My bad. Yeah, so we have a, we want to translate this problem into quantum. So, the first thing is gonna be to choose a function, right, a Boolean function. And I gave the example of like f of x is equal to, let's say 1 minus x. Okay, so that is going to, we're just gonna pass in x, and then we're going to get out x. Right? So let's go to this picture. Okay, someone asked why the x is just, why there's x on both sides. Okay, So if we look at a regular function, right, if I say f of x equals to 1 minus x, what happens if we pass in a 0 for x? Yeah, the output is 1. So that's what you get, right? So we have x, we have f of x right here. Okay, so x does not change, right? That sounds like a stupid question, but that is why our x here is still x. Does that make sense? We didn't change x in our order, in our order. Okay. So now y, you have y, and now you are saying y modulo addition with f of x. Why are we doing that? Okay. So first of all, we get why there's an f of x, correct? That is our output to our function. Okay. But we have to apply that output to some qubit. Okay. And in our case, that qubit is y. So we can't just say f of x is equal to y. We can't just replace the qubit. Does that make sense? We have to incorporate the original state that was on the qubit.
Why is it?
Yeah. Yeah. So y is going to be this qubit right here. So our input is y. And then our output becomes y modulo addition to with f of x. Okay. So all that means is, if you think of it, if you say, okay, I know that we're doing binary addition, Sarvesh, please stop saying that. Okay, so now all this is saying y, and you're adding that to whatever answer you get. Does that make sense? I thought that was it is XOR, and we showed how XOR, when you're dealing with binary operators, it's the same as addition.
Oh, yeah, it is, yeah.
So it is adding, yeah, instead of carry, it's rolling over. That's why it's modular. Okay, so that is all the oracle is doing. Okay. Now, how do we make an oracle, right? So we don't know any of the inner work. So this 1 minus x. Okay, does anyone know in binary terms, like in binary operators, how can you calculate like 1 minus x?
Like you make a negative number, so like what would you do? Would you do like one? For if there to be negative x, you have to put like two columns.
Okay.
You have to negate that's already not it, and then add one.
No. So basically, if you have 1 minus x, because we're only dealing with ones and zeros, 1 minus x just means not x.
Does that make sense?
Oh, yeah.
So 1 minus in binary. Okay. 1 minus, let's say x is 0. That'll give us 1, right? And then 1 minus x is 1. That'll give us. Did I just say the second one?
Maybe.
No, okay, 1 minus 0 is 1. 1 minus 1 is 0. Okay, that is normal stuff. Okay, so what that turns into is so 1 minus 1 is 0. 1 minus 0 is 1. So you see this x. This is our x. You see how it just flips? Our output is just the flip of x, like the not of x. So we essentially just transform this binary, this function, this math function, now into classical binary logic, okay, with using a simple not. So we can write this as f of x is equal to x, and I guess if you all know Java, you put a little exclamation mark. If you're doing here, we're just gonna put bar. That's gonna denote not. Okay. So now, we want to do this not operation, okay? And then we want to put that into a function, or save that value onto a qubit, okay? So firstly, how do we do a not? Yeah. The unitary is the quantum aspect. Okay, so how do we apply a not gate?
Actually,
Yeah, like how do we apply, how do we say not X?
like in quantum,
In quantum
X.
right? Because not is gonna be the same for classical or quantum, right? Okay, great. So we apply an X gate into our X value that we pass. I guess just two X's. So let's just call it the not gate for now. Okay, so we apply a not gate onto whatever we're passing in. Okay. So we'll just like X. Okay. So we are looking at that box, right? That is our oracle. So we apply an X gate. So now, okay, we're gonna start wrapping these up. But this is the last thing, okay? How do you save that value onto a different qubit? How do I transmit that value across? Not yet.
Not even close to that yet.
It's, okay. If my, how do I do it, what is this, okay. I want to incorporate 2 qubits in this operation. What kind of gate would do that? If I want to involve 2 qubits. Any multi-qubit gate, right? So a CNOT, you don't want to do it a CNOT, right? So keep in mind, we're still dealing with classical stuff. So a classical CNOT is just going to work in the way that you expect it to, right? If I do a CNOT controlled on my X, right? And then it's going to do a NOT on this Y, what does that do? It's my X input, or yeah, X input, right? If I control on that, and that is a 0, and I do a NOT operator on Y, it won't do anything, right? Since this X split to a 0, and apply a NOT on the Y, it does nothing. But if our after the NOT gate on this X qubit, after the NOT gate, if it was a 1, then it's like, oh, okay, I do flip the Y. Do you guys see how that act of flipping, which is the same thing as an XOR, which is the same thing as modulo to addition? Does that make sense why that's on this Y qubit? No worries, no worries. So, okay, to reiterate this, does everyone get how we made our function f of x is equal to not x? And we understood why we put this X gate here now. That is the equivalent of doing a not operation. Okay. So now, basically, we just did this part, okay? But this equals f of x, right? You don't think about this classically. It's like, oh, okay, I have an answer. But here we're dealing with individual like qubits. I have to save that answer somewhere, okay? So there's a second qubit that is waiting for us, this Y qubit. I want to save it onto the Y qubit, right? To save that answer.
And Y is our output register, by the way.
Yeah, Y is our output register. So that is why we're doing our operation, then our output is going to Y. So in this case, we are doing this CNOT operator, okay? If you're still not understanding why CNOT and why it can't just be arbitrarily any other multi-qubit gate, okay? Probably I'll take a bit longer to explain, but we'll definitely go over that next week, okay?
Yeah. So we completed basically a bit approaching half of this algorithm for our first week. And for next week, we are going to be completing the algorithm. So we'll be going over the next steps to do. So if we look at this over here, we're going to be looking at this portion over here, what it does. So after we do the unitary, we're going to be completing the unitary, looking between 2 and 3, and finally talking about what happens after 3, the measurement. So that's going to be next week. And thank you for coming. We'll see you then.
I will be staying behind if you guys have any questions.
Yeah.
I'm sure you guys do.
And I'll post notes and the recording promptly.